Here is an interesting word problem. A pirate's treasure chest lies 6 meters below the surface of a hidden saltwater lagoon. For this video, I'm only going to solve part A. What is the pressure acting on the top of the treasure chest? Well, the first thing we do is draw a picture to represent what is being asked of us. So there is a treasure chest at the bottom of a lagoon. So we'll draw the bottom of a lagoon here. There is the bottom of a lagoon, relatively flat. And on it is a treasure chest, rectangular in shape. And the surface of the lagoon is up here, the water surface. And it says that this treasure chest is 6 meters below the surface of the lagoon. However, it also says that the top of the pirate's treasure chest to the surface is 6 meters. So 6 meters starts from here, the top of the treasure chest, to the surface. That depth is 6 meters. In fluids, the deeper you go within a surface, the deeper you go within a water, or a liquid, I should say, a fluid, the higher the pressure. And this one here specifically tells us to find the pressure here at the top. Presumably, if somebody comes along and finds his treasure chest, they want to open the lid. Let's look at our equation now we're going to use for this. We're going to use equation 23. Pressure at 2 is equal to pressure at 1 plus rho GH. Now pressure at 2, that's what we're seeking for right here. Pressure at 2. Pressure at 1, well, that is the atmospheric pressure that is acting on the top of the water. Remember, we live in a fluid called air, and that air has pressure at sea level. That will be pressure at 1. And it's also known as 1 atmosphere. And while we have the sheet out here, the atmospheric pressure is 1.013 10 to the 5 pascals. It could also be written as 760 millimeters of mercury, or more commonly used as 14.7 pounds per square inch. And that is all equal to 1 atmosphere. So the atmospheric pressure pushing down on the water is 1 atmosphere. That would be P1 in our equation. Plus rho GH, and these represents the properties of the fluid that we are concerned with. In this case, it's water. More specifically, we're concerned with salt water. And rho is the density of salt water, and we have here density of fresh water, 1,000 kilograms per cubic meter, and the density of salt water, or seawater, is 1025 kilograms per cubic meter. Let's write the equation down here. This equation. Pressure at 2 is equal to pressure at 1 plus rho GH. And all of this is with respect to the fluid that we are interested in. In our case, it is salt water. And when I write this, P represents pressure, I put a little stem at the top of the P to distinguish that from the letter rho, rho representing density. So this is the pressure at 2 with a little stem is equal to the pressure at 1, that's a P with a little stem on the top. And pressure at 1 is the atmospheric pressure pushing down on the water, rho GH. Let's have a look at the units now for this. Pressure. All pressure has the units of a pascal. So pressure at 2 has a unit of a pascal. It's equal to pressure at 1. It too has a unit of a pascal. We go back here to our equations. Atmospheric pressure, this is one we want to use as the units of pascals. And then we have rho GH. Rho is density, that's kilograms per cubic meter in base units. G is meters per second squared, acceleration due to gravity. And H is the depth. and that's in meters. Let's look at this h one more time. 6 meters, h can represent height. H for height. And that would be the height of the water above the surface of the treasure chest, the height above the water, above the surface of the treasure chest, I should say. Or we can be looking at depth. It is the depth that of the treasure chest, the surface of the treasure chest, below the surface of the water. Either way, it all means the same thing, a distance. That distance right here. We're going to use the letter h for this distance for this equation. And it has the units of meters. So we have pascals on the left-hand side, pascals for the atmospheric pressure. And this combination of units, it can be reduced. This meter, since everything is multiplied, we can cancel out that meter, and meters cubed, we'll change that to meters squared. Cancel that one to one of these meters. Kilogram meters per second squared, this is known as a Newton. And in the denominator, we have meters squared. And this, the Newton per square meter, by definition, is a Pascal. So this combination of units right here, or of variables, has the units of a Pascal. So it's pascals, pascals, and pascals, so everything matches. Now let's have a look at what is given to us. Make a list of what is given. We're given the depth, or the height, letter H, equal to 6 meters. We know the pressure at 1, the atmospheric pressure. Even though it's not given in the word problem, it's definitely implied. This is atmospheric pressure pushing down on the surface of the lagoon. Pressure at 1 is equal to, and that is here, 1.013. And the unit is pascals. We want to find pressure at 2 at this depth. What is the pressure at the surface of that treasure chest? Pressure at 2 is, well, we don't know. Density. This is density of the salt water. And we go back. It's 1025 kilograms per cubic meter. And what else do we have here? G. G is understood. Gravity is all around us all the time, 9.8 meters per second squared. I think we have everything that we need now. And we'll look at the units, make sure everything is in the proper metric base units. This is a derived unit, and it's derived from the original base units. A Newton is also a derived unit, and it is derived from the original base unit. So everything here is in proper base units. Since everything is already in the proper base units or the derived units, we don't really have to follow the units when we do the actual equation or solve. We can just use the numbers. So I'm just going to go ahead and use pascals because everything here is in pascals. Make it look a little bit neater. Writing down the equation now. Here, pressure 1 plus is equal to pressure at 2 plus rho GH. Putting in the numbers now, which is the units of a Pascal. Pressure at 2 is what we want to find. Pressure at 1, that 1.013 times 10 to the power of 5 pascals plus the density of the salt water, 1025, times 9.8 times the depth, and that has the units of Pascal as well. Solving this in our calculator, this portion, pressure at 2 is equal to 1.013 times 10 to the power of 5 pascals plus 60270 pascals. Adding these two together, being careful when you use this in your calculator, this is 10 to the power of 5, it's not just 1.013, it is 10 to the power of 5. Pressure at 2, adding these two together, comes to 161,570, and the unit is a Pascal. Looking at the significant figures now, the original question where we're given 3 sig figs for the depth. That was the measurement down here. And everything else is understood. We'll consider them to be exact values. So we can have 3 significant figures here. Pressure of 2. 1, 2, 3. Look at that one. Go on up 1.62. 10 to the power of decimal point is here. 1, 2, 3, 4, 5 pascals. And now to see if this answer makes sense, the atmospheric pressure at the top is 1.013, 10 to the 5. And as you go deeper into a fluid, the pressure is going to increase. The deeper you go, the higher the pressure will be. So the pressure down here should be higher than the atmospheric pressure above, and as you can see here, that it is. So it's a reasonable answer. But we have one more item to concern ourselves with. Is this absolute pressure, or is it gauge pressure? The difference between these two is in another video. In our case, since we are including the atmospheric pressure, this will be in absolute, in terms of absolute pressure. So pressure of 2 is approximately 1.62, 10 to the power 5 pascals, and we'll write in here absolute. Let everyone know that we are including the atmospheric pressure.